I probably should begin with prayer to annoy YouTube, you know, just as a point of order. Let me pray again. Heavenly Father, we thank you again for this time we have to meet and just study your creation. Just help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So actually, I usually write on the board, but this is really informational, so I'm going to use the slides here for a minute or two. Although slides may be a bit of a stretch. So in Physics 2, we're interested, the proper title for the course might be electromagnetism, right? So it's the study of electricity and magnetism, which ultimately is centered around the question of charge and how charge interacts with other things with charge, like what's charge? Well, that's much like asking the question, what is mass, right? Well, can you guys tell me what is mass?
Just the matter that makes up something?
The matter that makes up something. It seems a little bit circular, but I'll take it. Anybody else? Can you define mass? It's kind of a trick question. I mean, mass is basic. It's a basic physical quantity. The mass that something has. There are two things you could talk about for mass. Admittedly, you could talk about inertial mass versus gravitational mass. Inertial mass being the property that an object has to resist a change in motion, whereas gravitational mass is the mass that gravitates, right? And those are the same mass, it turns out, right? Like that's one of the results of classical mechanics that we studied last semester. But at the foundation of things, I can't really tell you what mass is. It's something that objects have. It's something that physical bodies have, but it's basic. In the same sense, charge is basic. It's one of the basic physical quantities that every elementary particle has. Every elementary particle is either has positive charge, negative charge, or it's neutral. Current physics, there are basic particles called quarks. They have fractional charges. They've got a third of the electron charge or 2/3 of the electron charge. But those cannot be observed. Everything that we've ever observed, charge-wise, is an integer multiple of the charge of an electron. So this is an experimentally confirmed fact for a better part of a century. Every time we observe charge, it's in multiples of the electron charge. All right? So that might make you think that we'll use the electron charge as our fundamental unit of charge. Well, no, we don't do that. We use something called a Coulomb. So what's a Coulomb? So the electron is negatively charged. The proton is positively charged. The neutron has zero charge. Those are three basic players in this game. Now, for the most part, we don't think about protons, neutrons, and electrons. We just kind of think about abstract charges in here for a second. But protons, neutrons, and electrons would be examples. But anyway, the Coulomb is the fundamental unit of charge in the same sense that meter is the fundamental unit of length or second is the fundamental unit of time, right? A Coulomb is the fundamental unit of charge, and it is 6.25 times 10 to the 18th e. Now this little e is the charge of an electron. In other words, every electron has 1.60 times 10 to the minus 19th coulombs. In Physics 1, for the most part, we could get away with not talking too much about scientific notation. It didn't matter too much to us, multipliers. Here, it's lifeblood. We must understand how to work with large exponents and small exponents and use multipliers like milli, micro, nano. These things will come up, mega, all these things. So if you don't know your multipliers, that you should review. That matters actually a lot more than, say, momentum. Multipliers matter more than momentum for this chart. Getting back to your question. What will matter is basically Newton's second law. That's mostly it. Free body diagrams, we'll see that in a second. Anyway, so you would literally need 6.25 times 10 to the 18th electrons. That's more than the national debt in electrons to get 1 Coulomb of charge. That's how huge a Coulomb is. All right. So the electric force is the force that we find between charges. It's very similar to the gravitational force, but very different. It's similar in terms of its dependence on position, as we'll get to in a second with the Coulomb force law. It's very different in the sense that if you have two like charges, they repel. If you have two unlike charges, like positive, negative, they attract, right? Gravity, on the other hand, does what? It just, short of science fiction shows, it always attracts, right? Like there's like an episode of Fringe with like, you know, anti-gravity, which goes the other way, but that's just science fiction as far as we know. So gravity is always attractive. Electric force can be either attractive or repulsive. Some other basic things we should talk about here. A fundamental principle of physics is the conservation of charge. An isolated system has a constant amount of total charge. This is a physically observed fact. Another idealization we use in here, a conductor. A conductor is a material which allows for the free flow of charge. So in a conductor, charges can just slip around any different which way. They're completely free to move around. On the other hand, an insulator is a material which holds charge in place. So like the structure of the material is such that there are bound charges to the molecules and they're just kind of stuck there. So it's a different kind of thing. And of course, those are both idealizations, right? There are things that are kind of between those. And we're talking about a perfect conductor and a perfect insulator. Ground is a concept. It's essentially an infinite source of charge. In a circuit diagram, you denote that by something like one of these guys. Or it could be like a triangle sometimes for ground. So ground is, you know, it allows you as much charge as you want from the ground, free-flowing charge from there. For example, every house has a grounding rod, right? If you go out and you look at like the electrical box, there's like an 8-foot copper rod that's supposed to be driven down into the ground and a thick copper wire that attached to the quote-unquote ground of the house, right? It's important if you get struck by lightning. Anyway, don't do that. I did have a student get struck by lightning this summer, though. He was boating, and it like got him in the elbows. He said, like it hit the lake, and he was like with a bunch of people, and like it got his elbows. Somebody else had got him in the wrists, just like a little bit. So I don't know. Good times. So don't go boating. It's dangerous. Stay inside, really. You know, find yourself a Faraday cage. You know, that kind of thing. What's a Faraday cage? I don't know. We'll find out at some point. But anyway, so there's a process by which we may induce a net charge on a conductor. The way you do that is something like this. You take a neutral conductor, mind its business. You bring it near a negative charge, which we just have somehow. How do you get a negatively charged rod? Well, there's some materials that, like if you take this particular material, I don't know what it is, I forget the name of it, but you take some fleece and you just rub the fleece over the material. You can like kind of basically brush off the positive charge, and you can like make that rod negatively charged. So there are different materials that when you rub one on another, you'll get an excess or you know, either too much or too little charge. You can get a positive charge or a negative charge. Admittedly, annoyingly, this is all Benjamin Franklin's fault. When I talk about an excess or you know, too much or too little charge being positive or negative, the actual physical reality is that it's exactly the opposite, because electrons actually have negative charge, whereas positive charged things are, there's some weird ions or something, but like in actual wires, negative electrons are flowing opposite the direction of the conventional current. So we have this kind of annoying bad choice in conventions early on, but we're stuck with it, all right? So electron, technically, I should say, I was missing a minus, right? The electron charge actually is minus 1.609, 1.6 times 10 to the minus 19th coulombs. But I don't put that minus in the E. Like E I use as just an absolute number, 1.60 times 10 to the minus 19th. Much like last semester, we used G as the gravitational constant. It was 9.8, right? It wasn't minus 9.8. That minus we put into the equations by hand to, you know, indicate the directionality. Okay, same thing with E. It's a positive number. But the charge in an electron is nevertheless negative. So when I said, everything I said earlier, I should have been saying magnitude of the electron charge. So admonish me if you'd like, I don't know. Anyway, so if we play this game, we can attract all of the positive charge in the conductor. So in principle, the conductor has both positive and negative charge. In theory, what actually happens is it just has negative charge, and if you put a negative thing here, it's going to push all of the electrons to the other side and leave an excess of like not enough electrons here. And then if you connect if you connect the conductor to a ground, then you drain off the negative charges and then disconnect the ground, and then voila, you've got a charged conductor. I'm mentioning this because we're going to work a lot of problems with charged conductors, and I do kind of owe you some explanation on how on earth you would actually produce such a thing. This is how you could do it. Yeah. In the middle of the course, we'll get to circuits, which is, you know, for many of you, that's an interesting topic, right? Now, polarization is another thing we should think about a little bit. In an insulator, it may be possible to arrange the molecules such that you have effectively a net positive charge on one side and a net negative charge on the other. See, if the molecules are like this, if they're what are these called, dipoles, positive and negative charge like that, if you have them all arranged, then effectively it's like there's a positive charge on this surface and there's a negative charge on that surface. We can have that kind of thing with an insulator. And we can also put a net free charge on an insulator, much like I did with a conductor. Anyway, I guess I'm just trying to say this much, guys. If you actually ask the question of how you would create some of the examples that we'll solve in here, that's a far more difficult question than actually solving the example. So, because I'll say things like, imagine there's a charge fixed in space, right? How do you actually achieve that? No one knows. No one knows. But we're nevertheless going to work these problems. So, all right, let's get to it. Current is a flow, is the charge per unit time flowing past an area. We'll get back to current when it's time. Don't worry about that at the moment. So here's the real thing, Coulomb's law and the electric field. All right, so we draw a picture here. If I put a charge Q, all right, let's see here, I guess Q1 is what I'm calling it. So if I put a Q1 here, right, and I put Q2 over here, I got two charges, right? Then Coulomb's law tells me the electric force that one charge puts on the other. All right, so in order to set this up properly, we need to have like an origin. So we've got position vector for the first charge, the position vector of the, so going back to your question, position vectors. If you don't remember position vectors, you should review position vectors. They are vectors that describe the position of things. So here's an origin, coordinate system, yeah. So R1 and R2, the positions of Q1 and Q2 respective. And then we can use these position vectors. Well, I also define this script R vector, which is R2 minus R1. What's that look like? R2 minus R1. So I believe that's this guy, right? Am I right? If I'm right, it should be the case that R1 plus script R gives me R2. Does that make sense? R1 plus script R gives me R2. Yeah, that's consistent with this equation. So that's the picture. And what's the electric force on Q1 is what I'm talking about here. So I said the electric force on Q1 due to Q2 is given by, here's the formula. Right there, I'll write it down here too. F21 equals to minus 1 over 4 pi epsilon naught, parentheses, Q1, Q2 divided by the length of R1 minus R2 squared. And what do I got there? I said R12 hat. All right. So what did I say? This is the force on Q1 due to Q2. On Q1 due to Q2. All right. Let's see here. What is R12? Did I define that already? I should have just done this all from scratch. I wouldn't have to read my notes. I don't think I've defined R12, have I? Oh, here it is. Here's a picture for what I meant by R12. So here, R12 hat. What is it? It is R2 minus R1 divided by the length. So it's a unit vector, right? So there's another concept you should review. If you don't remember unit vector, that's look that up. All right. So is that script R? What I script R? I said script R was what in my context here? What was it? It was R2 minus R1. Yeah. So this is actually, another notation for this would just be what? This is really just script R hat is what this is. I'm not very good at doing script R, which is probably why I went to R12. All right. So if I suppose, so script R points which direction? So script R is like this, right? Yeah? So describe this formula. What's it saying? If how about this? If Q1 and Q2 are both positive, what direction would F12 go? So if Q1 and Q2 are both positive, you'd have a negative number times R12, right? So it would go the opposite direction. So this would be the situation. This would be F21, as I have it labeled. This is assuming that Q1, Q2 is greater than 0, right? But what's the situation here? If, on the other hand, if Q1, Q2 is negative, what happens?
It goes to the same direction.
Yeah, it goes the other direction. So use this one here. So this would be F12 if you have Q1, Q2 is less than 0. So there you go. This is the Coulomb force law. Right. Now I've written it in an annoying case. In the case what? In the case that like one of the charges, I've put neither of the charges at the origin, right? When the charge is at the origin, the formula gets easier to understand in some sense, right? So like, right, before I get to that though, we could also talk about what? Instead of talking about F21, we could talk about F12, right? That would be the charge, the force rather, of from Q1 acting on Q2, right? It would have the same magnitude, it would have, but it would have the opposite direction, right? So basically, F21 and F12, they're a third law pair. They're equal and opposite reactions. The electric force always comes in pairs like this, yeah, between the charges. All right. So let me go over here, talk about if we have Q, I'll put it at position, let's say R1. Then I can ask the question like, if I've got a little charge here, Q, like here, and that's at R, right? What would the formula for the force be on Q? Little q. So I do, let's see here, you don't mind, I'm going to skip the minus and see if I can just do it. So 1 over 4 pi epsilon naught. I've got my QQ. All right, I divide by the distance, r minus r1, let's say. So I'm not trying to like use the same formula again. I'm just trying to like reason through it on the basis of vector analysis here. So the point is that the magnitude of the force depends on the inverse square of the distance between the charges. And we need to have it attractive or repulsive depending on whether or not the charges have matching or distinct polarities. So the polarity of the charge is whether it's positive or negative. Okay, so what do I want here? Let's see. So if they're both positive, it's usually helpful for me to think about they're both positive. If they're both positive, I want the force to be like this, right? So I'm going to assume Q and Q greater than 0 just to set up the formula. And so what should I put there? I want like R minus R1, if you'll forgive me for this horrible, monstrous notation, but I want the unit vector in that direction, right? There you go. That's the formula for the electric force on Q due to the big charge Q. Yeah.
On that one, why is the script R vector going that way and not that one?
Because I defined it as such over there.
Okay.
Yeah, I mean,
On this diagram.
understand that on the basis of that picture. Understand this on the basis of that picture. I'm trying to start afresh over here. That's not wrong. It's just I think I'm about to do something over here. So listen, oftentimes I don't find this useful. Like another way to write this formula, which is nice, is you can write QQ over 4 pi epsilon naught. The length of R minus R1, instead of square it, cube it, and then just do R minus R1. So oftentimes I find this right here is a nice way to actually set up the formula for the electric force. The electric force here is also called the Coulomb force. This was discovered by, well, Coulomb. Now, there's something we can think about here, right? So you guys remember in physics 1 we talk about what? Force of gravity, right? Which is what? Well, mg, right? So it's like mass times gravity is the formula. So in the same way here we can think about the analog of g, right? So the electric force is equal to Q times E. So now I'm changing the game a little bit here. We're thinking of this as, think of as quote unquote test charge. So what's a test charge? So what I'm supposing here is that the charge Q is larger, it's much bigger, let's say, than the little q. And so the big charge here is there, and then this little charge is small, so it's small enough that it's not going to push the big charge around, all right? So basically we can probe the electric force produced by big Q by putting a test charge in different places, right? And by definition, that electric force produced by the big charge Q is equal to the test charge Q times the electric field. This defines the electric field in terms of the force. The force is the electric field really in some sense is the force per unit charge due to the electric field. Excuse me, due to the charge. So electric field is going to be, an important player in this game. This is the electric field. In this case, due to Q. So big Q here is the source of the electric field, right? Now let me give you the formula. If you look at the book, like most of what I'm writing in the book, you won't find this in the book. The book always It gives you hard homework problems, but doesn't give you the formulas which are what you need for hard homework problems. I lead with the ugly formulas because I think you should know them, because that's how you set up problems, right? You can't always put everything at the origin like the book does. But if Q is at the origin, right? What's it look like? That makes R1 equals to 0, right? Then what's the force is equal to Q over 4 pi epsilon naught. And then you just have R hat over R squared. And there you go. That's or if you like, the electric field in this situation would be Q over 4 pi epsilon naught R hat over R squared. And this, my friends, is the so-called Coulomb field. This is the electric field due to a point charge, right? And I placed it at the origin, right? If you want the electric field that's not at the origin, you simply replace R hat with R minus R1. So this is the field point, and R1 is the source point. In other words, the field point is where you're measuring the electric field, whereas the source point is where the electric field's coming from, the source charge, in this case, big Q. All right? But there it is. So it's the same mathematics as we studied with Newtonian gravity, right? Inverse square law, same thing. Now you might be wondering, what on earth is epsilon naught, right? Well, I have it up here. Epsilon naught is the so-called permittivity, right? You want to impress your grandma, you can call her up and say, hey grandma, you know what permittivity is? And then she'll say, like, I don't know. And you should be like, well, you should have gone to college. My grandma went to college. And then some of you be like, my grandma's dead. I'm sorry for all of these scenarios. But anyway, is that a microaggression? Is that a medium-sized aggression? What size aggression is that? I don't know. I am monetizing my YouTube videos this semester as an experiment on how many tens of dollars I can make. So like, I want to buy what? I want to buy a chalkboard, and like a chalkboard's like $1,300. How long will it take me to make that much?
A while.
A while, yes, I think. So
everyone to sub to your YouTube channel.
Yeah, please like and subscribe.
Yeah.
Yeah. So no, they used to try to get me to say that, but anyway. So it's the permittivity that is a particular property of the vacuum, and electric fields also propagate in mediums called linear dielectrics. A linear dielectric is a material which, for all intents and purposes, behaves like the vacuum, except it's not. It's a material. But the electric field and the magnetic field propagate in those, much like in the vacuum, weirdly enough. It's almost like the vacuum is itself a material. Much has been said about this. But anyway, in practice, like, if it gives you great joy to multiply 4 times pi times epsilon naught every time you do one of these problems, by all means do. But a fun and easy thing to remember is that 1 over 4 pi epsilon naught is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. That I would recommend using that for calculations. Yeah.
So to clarify, epsilon denotes permittivity, and
Yeah.
epsilon naught is specifically the permittivity of vacuum.
Yes, that is right. Epsilon naught is the vacuum permittivity, but epsilon more generically would be like a permittivity of a medium. And that is a story we'll come back to eventually. Maybe we don't do that. That might be like the junior level course. You might have to wait for like fields and waves to get into that. There is something else called the dielectric, which is kind of a pseudo-electric field that you can talk about as an effective electric field inside materials, but that is not this course. So my apologies. Okay, so here's an example. Woo. Find the electric force on an electron. And by the way, the later part of this particular PDF is like a really hard problem I got stumped on, and I say skip ahead. And I have the correction to like example 5 in here. Like I've crossed it out. So I try things sometimes, and sometimes they go badly. So this isn't, it's documented, all right? I did find in my office, though, the correction to example 5. If you're curious, I'll show it to you. I don't actually calculate it. Like the problem I present later in the notes here is too hard to actually work out. It's not hard to find these. Anyway, so this one is pretty straightforward. Find the electric force on an electron at that position from a proton at that position. All right, so here we go. I calculate the displacement vector from the proton to the electron, I think, R1 minus R2. And it turns out that they're the square root of 3 meters apart. Wait a minute. That seems kind of suspect. I don't think I need a square root there. If I'm, good grief. If this is a square, then this should be a square root. It shouldn't be here. It should just be 3. But anyway, this is still right because I have to divide by the length, which is the square root of the length squared. So this is the unit vector of that I wanted. Anyway, going down here a bit, here's the formula. So the force on the electron is as such. So the proton has positive E, the electron has negative E. And I think I'm following this formula over here for this example. And so when I crunch the numbers, I end up with, here's my 8.99 I was advertising a second ago. You got the electron charge squared. The minuses be canceling. So you're just left with that guy. And then why did I factor this out? Why did I put this over here? Why would I do that? What am I after? Every force is what? A magnitude and a direction, right? The direction's a unit vector. So if I write it as a unit vector times a number, then I know that that number must be the magnitude. So this is a unit vector. Check it out. A third plus a third plus a third. It's 1. So it's a unit vector. And as such, the magnitude of the electric force is 4.43 times 10 to the minus 29 newtons. And that's its direction. So if you have an electron and a proton that are about 1.7 meters apart, that's their electric force. It's pretty small, right? These forces get much bigger when the electrons and protons get like much closer, right? So one of the great mysteries that quantum mechanics finally gave an answer to is how atoms are even stable. See, because the nucleus of an atom's got protons in it, and then there are electrons, right? And electrons are negative, but protons are positive. So how is it, being that they're so close, that the proton and the electron don't just get sucked together? How is it that the electron just keeps orbiting, right? You'd be like, well, it just keeps orbiting. But then there's more to this story. Later you learn that when charges move, not just charges move, when charges accelerate, they radiate. So an accelerating charge is a charge which puts off what's called electromagnetic radiation. I'm telling you the end of the story at the beginning. This is the very end of the course. So how is it that, molecules stay put together, and how is it that they don't just radiate off the energy and crash together? Well, quantum mechanics basically answers that by saying, well, they don't. Which is not a very satisfying answer, but that is pretty much the answer. Anyway, so in contrast, if you calculated the gravitational force between the electron and the proton, same distance, the gravitational force is 10 to the minus 68 newtons, right? So electric force can be much, much larger than the gravitational force, even though it's very small, but compared to the gravitational force, it's ginormous, right? So, all right, so we'll be talking a lot more about electric fields going forward, but this is the basic idea, is that we think about putting a charge at a point, and from that we envision there being electric field flowing out from the charge, if it's a positive charge. And to test the magnitude of the electric field, we put a point charge, a test charge, and the force of the source charge on the test charge right? That is Q times the electric field, right? So this is one of the things we want to understand. We want to understand how to calculate the net electric field due to not just one charge, but say several charges. So as we go on in this here, say find the electron due to a charge placed at position 2, 3. So what do? I put my Q here. I put my test charge over here. I typically use R for the place where I'm measuring the field, like just XY. And so the script R, the displacement from my source charge to my field point, is R minus the source position, which gives me this. And that is the script R, and the force is just this. Where script R actually, I mean, it's generally speaking, it depends on which position you're at, right? So the formula here is actually, it's a function. It's not just a number, right? Like this is the electric field at the point XY. It's Q over 4 pi naught, this over that. Now what that means is the square root of, x minus 2 squared plus comma, oh, good grief. I got the formulas next page. Let me get to them. It's like, here's the formula. This is the electric field at XY due to a charge being at 1, 2. And I'm suppressing units, like technically fine. You're like, you should have 2 meters here and 3 meters here. Can we just like suppress units sometimes, please? Thank you. All right. At least one of you agrees, so that's enough. Anyway, so there you go. That's the formula for the electric field for a charge being at 1, 2, just like that. So we can set up the electric field like such. What if you had more than one charge? How would you find the electric field if you had like multiple charges? Well, you do this for each one, and then you add the electric fields for each one. And that would give you the net electric field. That's the kind of thing we'll look at like next time, all right? So just wanted to get us started today. I hope that makes some sense. If it doesn't, my apologies. But, well, there it is.